Right. Morning, everyone. So today's our last lecture. It's not really a lecture, but we're just gonna go over some tips for the exam, and I think the consensus was that we'd go over through the coursework, so we can do that afterwards. So very briefly, the exam is 1 hour and 30 minutes. There's 10 questions, which are a mix of open-ended and closed-ended questions. So your type of open-ended questions is describe, explain how something works, or you can compare how different protocols or how different approaches work. So there's a mix and match, whereas the closed-ended questions tend to be multiple choice, short answer, where you ask to match two sets of sentences, or you're asked to fill a table in the same way that you've done for some of the exercises and courseworks. So yeah, there's a mix and match, as I said. You probably will expect more close-ended questions than open-ended, so there'll be a sort of a healthy balance there. As I've said before, the style of questions is very similar to the examples shown in the lectures and the tutorial. And many of you have asked about calculators and other things, so here I'm sort of explicit about the fact that you don't need any calculator, you don't need to memorize any formulas, though you'll be expected to know how to apply certain formulas if those are given to you, or certain algorithms or methods, etc. So you don't need to memorize any reference figures or tables as well. So the one that came to mind is that IP had a structure, so you don't need to know those, but you do need to know certain key elements about the network layer, in particular the IP packets carried source and destination IP addresses, that these are 32-bit addresses, and sort of how they're structured. So in regards to the content, I would say to look at the exam tips at the end of each lecture if those are available. Otherwise, look at the material covered by the courseworks, which is sort of complementary to the lectures, and then the tutorial exercises. And just be aware that some questions in the tutorials will be sort of bonus material, and hopefully they will be marked as such, so those are mostly for your benefit, but they won't show up in the exam. And yeah, so try to get to the core of the key themes of each lecture and understand those well. And I think once you've done that, you'll sort of be very well prepared for the exam. So, there's obviously the exam cannot cover every topic. So, you can come up with your own strategy of how to optimize your time studying for the exam. So again, prepared for the exam by doing the tutorial exercises again, working through each of the courseworks, and if you're looking for extra practice, look at the book for extra examples, and you'll be able to find the solutions for those online in one of the main websites for getting books and things like that. And then I guess discuss those with your colleagues, and if you do all of that, you'll do great in the exam. You have nothing to worry about. So any questions about the exam before we move on to the coursework? Is that clear? So let me bring up coursework 1. Spec. Or actually, I should use this one instead. Right, so coursework 1, did everyone manage to do question number 1, or does anybody have questions? Unsure about the result? Otherwise, it's not very useful if I just run through the solution. I mean, maybe it is for some of you, but how would you rather do this? I mean, I could sort of do it live, but I can't promise I'll make no mistakes. Okay, so let me bring up the solutions and we can sort of discuss those. Okay, so for question number 1, you're given a set of parameters for the tandem network, right? And then you need to choose a value of x for the packet switch network. For the circuit switch network, you're given all the parameter values, so you just plug in that in the formula and you get 2.25 seconds. Yeah. And then you can choose any number for x. I think in this solution set they choose x equals to 1, which is fairly large, as you know. So you get sort of an absurd value for the total transmission time for the packet switch network. Yeah. And you can sort of verify those using the model simulator. Then for question 2, if you take on the same values, but in this case you want to figure out what value of x gives the same time for the packet and circuit switch network. So you're gonna make a nice equation and you're gonna solve for x, and that's, if you do that, right here, basically making those two transmission times the same, you have values for all the parameters except x, so you end up with an equation that you need to solve for x, and once you solve you get, this value up to 5 decimal places. Yeah. All good there? Who did not understand that? Did someone not understand that? No? Okay. So, third question. This is where we increase the message length by 2 bits. So in the previous questions we had to calculate the value of n. That came out as 10, and it was sort of the right fit. So if you added, and that's the point of this question, if you increase the message length just by a couple of bits, it's sort of long enough that it requires an extra packet to be sent through the packet switch network. And of course that, because each packet needs to carry a header, it's not only those 2 extra bits but also the header for the new packet, for the 11th packet. and so there's sort of a big increase in the transmission time for the packet switch network compared to the circuit switch network. So, as it says here somewhere. Right. So question 4. Again, we're sort of playing around with the values, understanding how the total transmission time changes as a result of the message length. And now that you have the 11th packet, if you just add another 2 bits, that sort of has a minimal increase or increment in the total transmission time, because you have the 11 packets being sent, the 11 headers, so you don't need a new packet, so the increment in time is the same as in the circuit switch network. Yes? So the increment is the same in each network. For question 4. Question 5 is not shown here, so I need I'm a look for it. So question 5. Right, so question 5, what's question 5? I think question 5 is comparing so based on your observations of the tandem network, discuss which other approaches would be more suitable for this type of network. So what's the consensus, if there's one? Circuit switched, can I guess show of hands for circuit switched network? Alright, packet switched network? Okay, 2-1. So I think because the network is relatively simple here, you don't really gain much by using a packet switch network, right? So in the second, yeah.
Is circuit switching used that much anymore, or is it essentially pretty much all packet switching?
Yeah, in the internet everything is packet switched, as we've learned.
Is there a case when circuit switching is still used there?
Well, it was used quite a lot in the telephone system, and perhaps some old telephone systems still use that. But yeah, it's a good question. I don't know actually. But even if you have voice over IP, it's packet switched because it's over IP. But so I think, yeah, a lot of the newer technologies will be mostly packet switched networks as they scale better, and allows you to get those more complex networks, topologies, and at scale as well. So, but I'll have a look. There might be still some. Yeah, I'm wondering if it's only old technologies or whether newer technologies use circuit switch networks. But I'll come up with a couple of examples. All right, that's good. So a specimen answer would be tandem network is relatively simple, so either would be suitable. So I guess it comes down to the value of x. If it takes out of that comparison between a trade-off between x and the connection time. If the connection time takes maybe too long, and you have a relatively small x value of x, so for making the routing decision, then perhaps the packet switch network might be more appropriate. Yeah, so one point that's made here is, yes, as you add more nodes, then as you add more nodes to the network, then you start to see congestion, and I think that's the point of of the star network that introduced next. So let's go back. So in version 2 we're looking at the star network. Let me get solutions again. Right. So again, now we have a new formula because we have a different network, so the total transmission time will be slightly more complicated to calculate, particularly for the packet switch network. As it says here, in the circuit switched case, there are simply 3 instances of the circuit switching times for version 1. So it's essentially three times the value of the previous network. So it's 3 instances of the equation from question 1. So if we plug in the values again, we get so 3 times the original value we got in question 1. Not sure what they're on about here about hops, but for the packet switch network, the total transmission time. So again, I think it explains there how you arrive at this formula, at least from an intuitive point of view. So yeah, so just plug in the values, and in this case, x is used. The value used for x is the one in question 2, so the threshold. So you arrive at a value that's roughly 1 second lower than the circuit switch network. And again, it's because you don't have that connection time that you need to set up for the circuit switch network 3 times in a row, that the packet switch network sort of wins this battle. Okay, so question 7. Under what values? Yeah, again, you end up with an equation to solve. You have the 2 ways of calculating the total transmission time for each of the networks, and it's just plug those in and you solve for x, and you'll get x that's about, and this should be an equality, I suppose. So in the previous case, x should be lower than 0.09375. In this case, x should be lower than this value as well. Right. So you sort of have more room to have a larger x compared to the simpler network. Right? So in the simpler network, the value of x was below 0.1 seconds. In this case, it's above 0.2 seconds. So it kind of shows the power of the packet network when you have topologies where you have sort of a centralized node, and sort of all traffic goes through that node, and you have congestion that results from everyone sending at the same time. In the packet switch network, things kind of break down into smaller bits of information, whereas the connection, you need to set up the connection every time, and the network needs to be free to allow that connection to occur. So in the circuit switch network, all nodes cannot be sending at the same time. Only one message can be transmitted at a given time, whereas in the packet switch network, they can all send at once, and then the node in the middle sort of buffers things as they come, and then it sends off when it's ready to send off. So questions 8 and 9 basically just had to use the simulator. Since they don't give you the formula for calculating the total transmission time for individual messages, or taking into account the value of individual messages. So in this case you'd have to use the network model sort of to get the value or the answer to this question. So if I remember correctly, so in this case, yeah, the third message, which has the smallest size, is the one that takes, that's quicker to arrive, but by a small time difference, but yeah, because the message is smaller, essentially has a smaller transmission time. And for question 9, you again increase the D this time. So I can't remember if in this case you end up with 2 messages of the same length. Straight away. Yes, in this case, because you have 2 messages that have the same length, it sort of goes through alphabetical order. I guess you assume that the message coming from A is queued first, so therefore is sent first to D and arrives before the other message, which has a similar size. Right? Yeah. As it says here, as this message is the first message in the network, it doesn't have to wait in a queue and can go straight away. Even though in reality there'll be some little time discrepancies there. Everything doesn't sort of get sent exactly at the same time, or there'll be little things that sort of shift the time and allow things to be queued sort of randomly. But I guess in this point is just to keep it simple. You assume that the message from A arrives first and therefore doesn't have to wait in a queue and go straight away, whereas the other ones have to wait for A to be sent, the first message to be sent first before they can be sent afterwards. Right. So any questions up until this point? No. Yeah.
Will the questions, is it important for us to look through this thoroughly because questions in the exam will be similar, or the style of questions, or like what, how will this be?
So for the packet versus circuit switching, part of the material is really what's important is to understand the differences between the 2 types of networks, and in which cases one could be preferable to the other, so the pros and cons of each type of network and the situations where one could be more appropriate than the other to solve a specific problem. Yeah. So it's not so much the calculations that matter, but sort of what you learn from doing these calculations about the trade-offs between the 2 types of networks. Yeah? Hope that makes sense. So question 10. I need to recall what the question is. So based on your observations with the star network, discuss one negative issue that you observed with this type of network, and whether changing this type of network could address that issue as well as introduce additional issues. So what's the key issue about this topology that the first topology didn't have? So all traffic has to go through a central node, right? And that can create congestion if all the sending nodes try to send at the same time, or they try to send at the rate that the node in the middle cannot process that information fast enough, so packets that might end up queuing. If the central node doesn't have enough capacity to store all those packets might be dropped. So we need mechanisms sort of to handle congestion and control the flow of packets through the middle. So I think in the first class we talked about other types of topologies, even though maybe we didn't cover this in too much detail. We talked about other kinds of topologies that we could have. So I guess you might have thought about what other topologies could be used instead, or what topologies might not have this problem but might have different problems. Anyone wants to suggest something? So examples of other, yeah?
Well, I suppose there is not network if the central node goes down and then
Yes.
this connections.
Exactly.
Whereas if you had a ring network,
Mhm.
one goes down to just one.
Yeah, that's a good example. So in the ring network, you didn't have the same problem. You'd have other problems, I suppose. But that's an example of an alternative network where maybe congestion wouldn't be such a key factor. So an example answer for this question would be, so I guess if you're worried about congestion, then you might consider a different type of network. So one that doesn't have that funneling into the central node and creating the bottleneck. So actually it doesn't really suggest that topology. I think as long as you are aware that there are other topologies, you could even possibly the most resilient to this type of effects would be the mesh network, where you have multiple connections. Even if one of those connections dies, you'll have other routes possible between any two given nodes in the network, so that'll be a most resilient type of network. Whereas your token rings or bus type of topologies have their own problems as well. So I think a good tip would be to briefly look at the different types of topologies and sort of try to understand what the pros and cons of those are as well. Is that okay for coursework 1? Yeah, cheers. Okay, so let's look quickly at coursework 2. I think here it would be interesting to maybe do this rather than just showing the solutions. I did this yesterday again, so I'm hoping it's still fresh. But I actually did not bring the piece of paper when I did it. So I just need some tables to fill in. So maybe give me 5 while I try to find a way to do this. And if you want to take a break, we'll come back at 10 past 10 to do this. I'm just going to figure out a way to bring up a table which we sort of can fill as we go for each of the algorithms. Yeah, so feel free to take 5 if you want. Grab a coffee or a tea or whatnot. Sorry, I didn't understand it.
Will the course answer hello to the cameras after class?
The solution?
Yeah.
The solution, I'm still checking where I can give this to you because this is
Got it.
sort of not mine.
Yeah.
So I need to check with the person from last year whether I can send this.
Can I check it?
Can you check it?
Yeah.
Oh, about the previous coursework, of course. Yeah.
I'm not sure the answer.
So here you don't discuss the network topology, and that's sort of the key thing we want you to look at is understand the pros and cons of each network topology. So this network topology has a downside that congestion would easily occur because you have the central node, and if all of these try to send at the same time, this will create a bottleneck, and if G is not able to process that information and forward that information fast enough, then the network will struggle to cope with the large amounts of data being sent through. So we talked about other types of topologies, so you might consider a different type of topology, and it might solve the congestion problem, but it might introduce other problems. So this is where you sort of compare the different topologies and the advantages and disadvantages of each approach. So whereas here, it's really talking about other types of topologies, if that makes sense. Yeah. Let me see if I can. Otherwise, I'll.
Could I use the value?
If x equals to 1. Yeah, I think for 6 you can use any value of x, right?
Can we bring a water paper and a pen for calculations during the exam?
Yeah, that's a good point. So the exam will be done online, but I suppose you can bring pen and paper if you need to sketch something out, or what do you call it? If you need a blank piece of paper to make notes, yes, I think that's okay. But I actually don't know. So maybe the best person to confirm that would be at the reception, the School of Computing reception on floor 2.
So we can't bring calculators?
No calculators, because you don't need calculators. The exam doesn't.
Will you send us the coursework answer?
I'm not sure yet that I can, because this doesn't belong to me, so I need to double check that I can send.
Okay, thank you.
But if you have your answers, you can check that your answers are correct now. Yeah.
Thank you.
No worries. So not sure yet. I'm not sure I can. Yeah, so I'm not sure I'll be able to upload the solutions to the coursework since these not really belong to me. I've asked the previous lecturer about it, so I'll let you guys know if I can. But at least you'll be able to check your solutions during class today. And hopefully that does the trick. Okay, so coursework 2. So begin with Dijkstra's algorithm to compute the least cost route from node A to all nodes. So we start at node A, right? So our set of nodes just contains A for the moment. We know the costs to our neighbors, which is set to 5A, the cost to B, and 1A, the cost to C via A. And infinity for the other two nodes we cannot reach just yet. So in step number 2, we sort of move on to the node of least cost, and that was C. So now looking at it from C's perspective, we add C to our set of known nodes. From C, we can see D. We know the total cost is 1 plus 1, 2 via C. So A can get to D via C with a cost 2, or it can get to B via C with a cost 3. Right? So it doesn't see E yet, so that stays at infinity because C doesn't see E. Now from C we move on to D because it has the least cost in this row, right? And we add D to our set of nodes. This is kept the same. This is kept the same as well. And what we see now that we didn't see before is node E, which has a total cost of 5. So from A to C to D, and D to E, that's a total cost of 5. So from here, where do we go next? So we go to B because it has a minimum cost after D here. So ACDB this cost. So we add B to N, and we've seen that actually arriving at E via B is less expensive or less costly than via D. So we update our cost to E, total cost of 4 via B, and in the last step we sort of add E to our list of nodes and nothing else really changes. So all nodes now in N, so we finish our loop there. Is that okay? So that was question 1. Question 2, the distance vector algorithm. So this one, we have 3 iterations. So step 0. So what do we do in step 0? Each node sees its neighbors, yeah. So okay, it's a bit slightly trickier to see, but if we look column-wise first, so A sees C and B with their respective costs. B sees A, C, and E with the cost shown here. Same for C, A, B, D. C is the most central node. And D only sees C and E, and E sees B and D. Alright, so first iteration is fairly easy. So second iteration, what do? We go 2 hops. Yes? So B and C stay unchanged, but now we can see D and E. So you can see D via C, total cost of 2, and you can see E via B with a total cost of 6. B can see A, C, and E the same. In addition to that, you can see D via C with a total cost of 3. C can now see E via E with a total cost of 3. And D can now see A and B, A via C with a total cost of 2, and B via C with a total cost of 3. And A, because this is sort of symmetric, stands up is a symmetric matrix, this will be sort of the inverse of that side. So E now sees A via B, again cost of 6, sees 1, and D directly, and C via B with a total cost of 3. Alright? So step 2, now we look at 3 hops, and I think pretty much everything stays the same except for the connection between A and E, and that's the same or similar except via different nodes. So A can see E via C, right? A, C, B, E, and B can see A via B and C, so E, B, C, A. I think everything else stays the same, right? I think so. So yeah, I think the initial example was slightly more complicated, so this is a bit easier in comparison. Right, so briefly comment on which algorithm was more efficient in this exercise and what other factors might influence the choice of algorithm. So what do you think? If you had to choose an algorithm, which one have you chosen? Yeah. Why? Yeah. And why is that? It's a small network, so knowing that the state of a small network is fairly low cost and easier to do. So that's kind of the reason. So for a larger network, you might prefer the distance vector algorithm because it sort of can track the changes that occur locally, whereas Gister's algorithm might be sort of very computational, or not very computationally efficient. And I think that's sort of highlighted here it's computationally easier to calculate and hold all the network knowledge in a small network. So other factors that it might bring up as well are the variation in the costs between the network. So the distance vector algorithm needs many iterations to find sort of the best cost, because there's a big difference between the costs and the links. And so theoretically the number of iterations that the distance vector algorithm needs to converge to an optimal solution will sort of be close to the maximum path size in the network. But if you have smaller costs, then that doesn't need so many iterations to get to that optimal solution. And yeah, again, it depends as well how quickly those values might change over time. So a distance vector algorithm can respond to changes sort of locally, whereas just algorithm needs a complete recalculation when there are any changes. So if you have things sort of, you work in a very volatile network, then the distance vector algorithm might be a preferable solution, as exactly, because it tracks local changes more quickly and it doesn't need to update the entire table at once. Is that all right? Yeah. Okay. Okay, so last question. How would you compute the list? Oh no, it's not, we have two more. So how would you compute the list hop routes for each algorithm? So what do we do if we just want to figure out the minimum number of hops between each pair of nodes? Right, so we set to 1 the cost for each link in the network, and then we just sort of compute the lists. So if you want to get from A to E, the list amount of hops is 2, so A, B, E. So I suppose for whatever reason you might want to minimize the number of hops rather than the cost. If, for example, you have very long links and you might want to minimize the propagation delay rather than but I think in practice that doesn't really happen. You just sort of use a different costing function. But I guess the point is you can use different costing functions, and the number of hops being the simplest one you can use. So 5, assume you are maintaining a network that uses the distance vector algorithm to calculate packet routing. Several machines on the network are suffering reliability issues. Discuss how this might impact the efficiency of the distance vector algorithm, and discuss the solutions. Is that the same or similar? So what happens if there's reliability issues? What if there's congestion and two networks cannot communicate? If a link is impaired and essentially useless? So I think, right, so it's not here. So Ian talked about this briefly in one of his lectures. So he mentioned the count to infinity problem, right? So This is where the cost of reaching an unreachable router gradually increases by 1 up to infinity, as the node cannot sort of find the offline node. Therefore, increases the cost by increments of 1, and so that it can take a long time to figure out that the link of the node has gone offline. And two possible solutions discussed here. So instead of using infinity or a really large number, you just use the maximum cost that you know of in the network, and you increment that by 1, and essentially you bring infinity to a much smaller number. And so when that gets incremented to 1, the router is sort of marked as unreachable. This is known as convergence time, but will have the opportunity to ask Ian more questions about this afternoon in the tutorial. I'll talk about that in a second. But one other solution is, I don't think this was covered in the lecture, so I think the point here was for you to just go in the book or look online and try to figure out what solutions out there, different approaches can be used to address this problem. So one of the solutions is known as Poisson reverse, so the algorithm prevents cyclic routes, so routes that loop back to themselves. But this is our sort of bonus material. They're not really expected to know this for the exam. So yeah, I think important here is to understand that the count to infinity problem can arise, and maybe suggest a simple solution based on the lecture notes. And the what circumstances that can arise. Right? Not really expected to know all the possible solutions to the problem, but at least one simple solution would be nice. And that sort of concludes it for today. We have 2 more tutorials. We have a tutorial this afternoon, which will be led by Ian. Ian is in the States right now, so this will be a Zoom call. So I'll send out the details for the Zoom session in an announcement. Hopefully that's okay with you. But yeah, I think since he's delivered the transport layer lecture, I think it makes more sense that you hear from him in the tutorial than from me. So you'll get the chance to work with him. I'll be around just to make sure there's no teething problems or operational issues. Everything sort of ran smoothly, but yeah, do show up and ask Ian as many questions as you want. And then tomorrow we have a tutorial. Will be about the lecture on Monday, so the application layer. And yeah, after that, you'll be ready for the exam, hopefully. So yeah, that's all for today. Thank you, and we'll see you again tomorrow morning. All right, have a good day. Cheers.